Since it's 2 o'clock, we'll wait a few seconds for folks to sign on, but I thought I'd start on time because your time is precious. My name's Darlene True-Christ, and I am the Community Engagement Manager at OOI. And it's really our pleasure to welcome Tim Crone. He's a Lamont Associate Research Professor, and he is also the chair of OOIFB's Data Systems Committee, and he is going to really teach us a lot today about how to use OOI data in the cloud with Pangeo. And so our intent is to make this as interactive as possible, and please don't hesitate to raise your hand or have questions in the chat, or simply interrupt Tim when and if you have a question. So with that, I turn it over to Tim. Thanks, Tim.
Thanks, Darlene. So as you can see, I'm adjusting my presentation as we go here. Please let me know if you can't see my screen. I'm showing my Jupyter Hub notebook here, which is where most of the presentation is going to take place. And I just also wanted to point out that, as Darlene mentioned, this is supposed to be really interactive. It's supposed to be a follow along kind of workshop where I basically type things into JupyterLab and you type them in too. So we type them together. If this is going to go very slowly, you're going to have error messages. You're going to raise your hand and tell me that you have an error message, and I'm going to fix it for you. We have almost 2 hours here, so we have plenty of time to, slowly walk through a bunch of really cool things that we can do now with the new Data Explorer's backend and JupyterLab's front end and OOI data. And so I just wanted to impress upon you the need for there to be a lot of interruptions and a lot of interactions. So let's see here. Onto the introduction markdown page. This workshop was helped a lot by Rich, who's another member of the OOI Facilities Board Data Systems Committee, which we'll talk about in a second, Dax, as well as Philippe, who's on the call. We're both on the call. And let's see, before I start talking anymore, I'm going to have some introduction discussion about the facilities board and the DSC, and also a couple of background slides about big data and OOI data. I wanted to make sure that everyone on the call has a couple of things going. One is that you really can't get into the Pangeo binder hub without a GitHub account. That's how you authenticate. So if you don't have a GitHub account, go get one. It doesn't take long. I think you just need an email, make a password, something like that. And so you have a GitHub account. And then, or if you don't want to make a GitHub account, you just want to watch, that's also fine. And then after you have a GitHub account, or if you have a GitHub account, I would like you to please go to this website here. I'll put this into the chat window. This is the repo for this workshop. So the repo for this workshop is here. Chat that to you. Got a lot of things that'll show up in the chat, including this one here, which is my first chat. This is the repo, and the repo doesn't have a lot in the README, but it has this link down here, and that link is to the binder hub. So this binder hub will take you to the Pangeo binder. It'll launch a JupyterLab for you, and it will pull all of these files and notebooks into your space on that JupyterLab. So just to be aware, your work on this JupyterLab is going to be ephemeral today. It'll go away since the binder. It's an easy way for you all to just log in, for large groups to log in and to use JupyterLab together as a group if you want to continue working on this, I encourage you to join the OOI Cloud organization on GitHub, and then use one of our Pangeos that we have available where you can work into the future and have your data be saved. But today you're just going to be logging into a binder, and that means that when you leave today, your data are going to be, or your work today is going to be gone. But all the work that you're going to work on is here in this repo. So like the notebooks we're going to follow along with are here. So like the first one we're going to do is this Spot PT notebook. That's there. And if for some reason you don't want to really do this, or you just want to click through it, you can actually click through it, but I'd recommend you type along with me. Or if you get lost or something's not working and you want to cut and paste something out of it, that's also fine. Whatever you want to do. But I do this kind of format with my classes in research computing and neurosciences, where we all sort of type along and everybody kind of flails together, and it's a group flail, and it's really fun to flail together. It's very it's a learning experience, and everybody is welcome to learn and flail and have fun. Section about the facilities board and the survey, and then we'll come back. So the survey, so the data systems committee is this committee that was set up by NSF that sort of sits kind of like a subcommittee of the OOIFB, the facilities board. And I copied a little something out of our charter for the users, or for the people on this call today, because the data systems committee is really responsive to the community in many ways. The goal of the committee is to, in part, this is one little teeny tiny piece of our charter, engage with the user community through meetings like this one, surveys like we'll talk about in a minute, and through other means to better understand the needs of the OOI community in terms of data, and to facilitate the promotion of a positive user experience. So that's why we're having such a positive user experience today. People on the committee are me and Karen and Richard Dewey from Ocean Networks Canada, Kristen Fogerin, Jim Patemra, Mary Jo Richardson, Rich Signal is on the call today, and then there are OOI appointees, Orest Kauka and Craig Rizian. You can contact any of these people regarding OOI and OOI data systems, and we're happy to hear from you and happy to learn more about what you are experiencing, what you're needing, what you're and how you would how you think the system could be better. In addition to those kinds of methods of contacting us, we just released a survey for the community. This is our second survey that we were running for the OOI community. There's a link for the survey that you can take, or you can just point your phone at this QR code and take the survey about OOI and OOI data systems, and send those to your friends and colleagues. We would really enjoy hearing from you about your experiences with this survey that we've been working on for the last 6 months or so. Okay, so that's data systems committee stuff out of the way. Does anyone have any questions about that? All right. Who is on the Binder Hub? 1, 2, 3. How about who's not on the Binder Hub? Who wants to be on the Binder Hub that's not on the Binder Hub? How about that? Nobody.
You're all free to unmute yourself.
Yeah, free to unmute.
Looks like everybody's good, Tim.
So let's talk real quick about Pangeo and OOI data and working with big data in the cloud. So as many of you know, data in the geosciences is really exploding, and the amount of data that we're all being asked to deal with is growing day by day. Here are a couple of really interesting graphs. One of them shows projected NASA cloud storage that's going to go into the hundreds of petabytes in the next few years. As many of you know, the climate model outputs that many people work with are many, many hundreds of petabytes now. And of course, the OOI system is now approaching approximately a petabyte worth of data that they share, if you include the video data that is on the raw data server. So this is a big problem for a lot of people in the earth sciences, and it's something that we've been working to solve through the Pangeo project. And I want to point out with this graph here, and something that a lot of times we always, I think sometimes gets overlooked. This whole system here, right? This fiber optic cable system with all these nodes and all these instruments was not designed and built for scientists to go and look at one single instrument. That's kind of what we're going to do today. But if you go and you look at one instrument, that's fine, and that's helpful, and I'm sure you can. That's possible to do science with one single instrument. But systems like the Neptune Observatory that's shown here, and the OOI Observatory that's shown here, other systems that are networks of connected instruments that span large spatial areas, are really designed to give synoptic views and deeper understandings and insights into Earth processes that require the analysis and processing of very large amounts of data from many, many different kinds of instruments. And so I think that, you know, it's easy to think that you can sort of do science with a downloaded data set with OOI, and I think you can. But if you really want to unleash the power of a system like OOI, you have to be able to give users the ability to look at various processes that collected by many, many instruments over time and space. And when you have data sets that get really large, if you look at those data sets like that, it starts to get really hard if you start thinking about downloading data. Okay, and so if that's the case, how should scientific data analysis infrastructure be organized in this new era of petabyte data? So many of you are familiar with a file-based approach. This is sort of the way that OOI started out working, and it's sort of still working now, although we're kind of transitioning away from this, where you have files on a server and you download data to a local disk and then you process the data locally. So there are server-side database paradigms, which were used a lot more earlier days and are becoming more common as well now, and where you have big server-side databases with server-side data and you query them, and this works well for lots of different industries, like the banking industry, where you have queries that are very well defined, but it's not as good for a kind of interactive, exploratory and curiosity-driven workflow that we often try to encourage in the sciences. So what's the kind of solution to this? It's a cloud native approach where you have data that's in the cloud, preferably stored in object storage and shared using cloud-friendly data structures and data organization, chunking, etc. And then you have, and you bring to those data in the cloud, proximate to the data, or at least in the cloud, maybe a cluster of workers or a worker machine in the cloud where the data and the processing happen next to the data. The data and the processing happen together remotely. So you bring your compute to the data and then you interact with those data and those output through just a web browser like we're going to do today. So we're going to kind of work like this today, although what's happening on the back end is not quite an object store, but we're sort of working with the OOI data as best we can to make it a kind of seamless remote data interaction experience. And Pangeo is really, what is it? It's really just a community of people who are interested in making computers work like this a little bit better. Making data, large data, work better for scientists. Big data that works better by working in the cloud, so that the download model doesn't have to be used anymore. So at its core, the Pangeo architecture includes some sort of distributed storage system, preferably in the cloud, doesn't necessarily have to be, some kind of a compute system that's probably or preferably in the cloud, or could be on HPC. And then that those data and those systems are interacted with through a browser. The Pangeo system includes tons of packages that are available with in Python. Right now, we're really Python focused, although we're not necessarily Python exclusive. I think the goal is to have or think about a future where any kind of programming language is supported. We're looking a lot now at Julia and the ability of Julia to support really large scale computing tasks. But right now, a lot of the really helpful, really useful scientific data packages are in Python. So that's where we're sort of focused right now, along with Jupyter Lab, which is a nice place of doing work. And so I wanted to point out a couple of our favorite packages that we use a lot. One is Xarray, where you can store and process and do work with large data sets chunked out in time or space, depending upon what works for you, and can contain lots of different variables and over lots of different coordinate systems, all sort of together in a happy little family that makes analysis, plotting, and visualization and insights really easy. And then also Dask, which I don't think we're going to get to today, but Dask is a really nice way of parallelizing distributed processing tasks. A lot of tasks in the earth sciences can be really easily distributed this through Dask and Dask methodologies and through cloud workers and clusters of computers in the cloud, as opposed to maybe some problems that are best supported by HPCs. A lot of geoscience data processing tests are really well supported in this environment, where you can just basically independently fire off a bunch of computers to do little bits and pieces of a job. And then the Jupyter Lab interface is a big part of this right now, which is a really cool place to work, and we'll work on this in a little bit. All right, so finally, back to this approach here. What can OOI do, and what is OOI hoping to do in the future? I think from the Data Systems Committee's point of view anyways, a goal is to, as a first step, make OOI data more cloud friendly. And that means have the data stored in object store or some kind of an object store like environment. It doesn't necessarily have to be in an actual, certainly doesn't have to be in a commercial cloud system, but to have the data approachable from a cloud compute platform that some workers might bring to the system, so that they can access data through byte range requests and other kinds of cloud-friendly APIs that will allow the use of cloud compute clusters with these data before we get to the point of actually supporting compute in place for OOI. So I just want to stop there. There's tons of slides, but I don't really want to make this a Pangeo talk. I want to make this an interactive session. If there's any questions about this, please jump in.
Hey, Tim, maybe it's not really a question, but just if people are thinking that this is, this Pangeo thing is sort of this kind of weird thing that, it's like some NSF project that like some academics are using, and now we're using it or something. It's really much more than that. And you may hear people talk about things like Open Data Cube or Digital Australia or Digital Africa or Digital California, and they're all using this approach. They're all putting their data on the cloud in analysis-ready formats or cloud-friendly formats, and using this sort of open, completely open architecture, very flexible, powerful architecture that Python has given us to basically transform the way we do science into something that's totally collaborative, encourages more people from different countries to use these tools. And it's like the way that, it's the way of the future. So it's really like we're plugging into this. It's not sort of like some weird exploratory thing.
Yeah, that's a good point. And I think the world is not only kind of moving toward this kind of paradigm for data processing, but it also has these really interesting new APIs for accessing data that hopefully one day could replace ERDAP like the EDR, and then also really interesting new cataloging systems like Stack, and then those that work with those kinds of systems like Intake for cataloging data and making the data access really more transparent for the user, so that people don't get siloed into their own portal for data, right? That the access for data becomes more uniform, egalitarian, and less siloed. We're going to talk a little bit about different ways to search multiple ERDAPs later in the workshop today, which is an example of how you can have cross usage of systems inside of a system like Pangeo. Any other questions?
Tim Melanie has a question.
Okay.
Yeah, thanks. Hi. For those who don't know me, I'm an associate professor in physical oceanography at Oregon State University, and my group does work with OOI data, but not through this system. Craig works partly with me. And I'm familiar with Pangeo. Now, haven't used it, but from the town hall workshop at the last Ocean Sciences in-person meeting in 2020, and from my work in the satellite community. And when I went to that workshop, and when I kind of inquired with colleagues about it afterwards who are involved in the development, it was at the time, it was kind of like, well, it's not really set up for, or the codes weren't really available to work easily with data other than gap-free, what they call level 4 data in the satellite community, or the modeling, the global model. And so it sounds like things have moved forward, and maybe this will become clearer in your example, but I'm just curious if you could comment on how much work remains to be done to provide the ability for people like maybe new grad students to come in and easily be able to work with these kinds of time series that have NANs in them. They all start and stop at different times, like things that, I'm used to, but I grew up in MATLAB. So like, I want my students to be able to do the modern thing, but I'm still learning the modern thing, and I'm not really capable of teaching it to them yet. And so like, is this still like, we're not there yet, or has a lot happened in the past 2 years that I don't know about, and it's ready for prime time now for this kind of data?
Well, this is what I use pretty much exclusively. I think it's ready for prime time. It's obviously, there's lots and lots of things left to do. It's a constantly evolving place, which is probably the more frustrating thing is that things change so fast, and there's so many package changes that that could be really disorienting for people. But my sense is that some of that toil that you talked about is still required. We're going to do a little bit of it today, because not all data systems are organized perfectly so that people don't have to do toil, data related toil. But we're getting better, and that's the whole goal.
Yeah, no, it's not that so much. It was more like, yeah, okay, I'm just gonna wait and see your example. It sounds like things have moved on a lot since I last knew.
Well, yeah, I mean, we'll take a look and see what you think of what we've done today, and I'm happy to continue this discussion. It's very interesting. So I'm going to share. I got back into the binder, which is nice. Need to be in the binder personally. I'd like to be here. So now I'm sharing my binder. Hopefully this looks a lot like what yours looks like. All right, so you would have logged into Finder. It will say Hub, AWS, US West up here, and you will hopefully have automatically have pulled the repo that we looked at earlier. So all of those files are in here, including the notebook that we're going to work on today. Rather than clicking on this notebook like this, what I would prefer that we do together is to instead start a new notebook. Okay, so here begins the interactive part of this workshop. And if you could click on Start a New Python 3 Notebook so that it looks blank like this, then what will happen is I'll just sort of start typing and hopefully you can follow along. And if you really don't want to do it, you can just click through this guy over here, or if you want to, you can cut and paste from time to time if that makes you happier. You'll enjoy the copy and paste. I mean, you'll enjoy the actual typing process. And then also, if you need me to change the screen size or change the text size, I'm happy to do that as well. So what we're going to do today is we're going to use something that Rich, Fernet, and Philippe wrote called EarthPy to directly access data in the new OOI Data Explorer, and pull it in, turn it into an X-array, and start plotting and looking at those data. So the first thing I'm going to do is I'm going to find some data on the OOI Data Explorer. So let's talk about how that's done before we actually start typing. So let's say we want to look at some bottom pressure data from OOI. I can click on this link down here to get to the Data Explorer. It's dataexplorer.oceanobservatories.org. And this is the new OOI Data Explorer that we have, that the OOI program has been working on over the last year and a half or so, or 2 years, which is a really nice new interactive system for finding data. And so I wanted to show a little bit about how you would do that and how you would get the information that you would need in order to access these data directly without having to download them. So here we are in the Data Explorer. If you click on Data Access, we know that we're going to look at bottom pressure data, and we're going to look for bottom pressure data from the central caldera of axial seamount. So here it's given us 12 different data streams from that include bottom pressure data. We're going to take this first one here, this bottom pressure tilt. Oh, no, actually, no, we're not going to do that. We're going to take this one, the first one that's a data product here called seawater pressure, bottom pressure. So we'll click on that. And this will take us to a page that will plot some of the most recent data that came from this instrument. So this is the data from the central caldera connected to this medium power J-box. And if you scroll down here, you can make this this plot show all the data that's available all the way back to when, just about when OOI started, which is in 2014. What I wanted to focus on today are some data that are surrounding this eruption here. So this is a big change in the bottom pressure associated with the eruption, the last eruption of the axial seamount. So how do we get the data that we want out of this system? There's lots of different ways to do it. You can download data like through like a CSV or a NetCDF. You can go to the EarthApp server and look at the data there, or you can just download the data directly using EarthApp. So if you click on station right here, this will bring you to the whole station, which has all of the different data streams that this particular station produces. And it will show you all the different data streams. such as the tilt, different directions, pressure, all of this sort of stuff. Okay. But what we need, all we need really is this guy here, right? We just need the URN. This is the data data set ID, I think is what it's called in ERDAP. So if we have the data set ID, that's basically all we need to get all of these things from this instrument. And we're going to use that in this next, once we click over to the Jupyter Lab. Okay. So let's go to our new, brand new we'll say the data set ID equals this thing here. So I copied that off of this page here. And I can chat this to you. This page is in the chat. You can scroll down here, click on that, copy it, and put it into your window as the data set ID. And next, let's go ahead and start importing some things that we need. We'll import pandas as PE. We'll import Xarray as XR, like we always do. Okay. And we'll import this ERDAP class from the ERDAPI package. So from ERDAP, 2Ds import, and then this is all caps, EAREDAP. And we can say that we want the server to be http:// ERDAP.data explorer .ocean observatories .org/ and we're going to have the protocol be tabled out. And we're going to say something. Let's go ahead and run that. We'll say something like E equals this ERDAP class with the server equaling the server and the protocol that we just defined. And then we'll say that the e.dataset underscore ID equals dataset ID. So I didn't run this cell up here. I need to run that cell to make the data to define the dataset ID, and then I can do that. All right, so that's it. We've got this ERDAP object, and this ERDAP object is set up to give us data from all of OOI. There's nothing that we've defined yet. Boy, actually, no, that's not true. Previously, we defined it to access data from all of the ERDAP server. And then once we put in this data set ID, we narrowed it down, in this case, to one data set ID, which is that single bot pressure and tilt instruments ID and all of those data that we looked at previously. Let's go back here real quick, because there's something really cool here that I forgot to show you. If we go back to here to the instruments webpage, you can click on inventory to see all of the data that's available. So you have things like the X and Y tilt and the bottom pressure, which is what we're going to work with, and the amount of data that is available over these sort of time periods, going all the way back to 2014. Lots of really interesting things in the annotations page. Giving you information about certain things that happened to the bottom pressure sensor. For example, there was some kind of a tilt releveling process that may be messing up data during these time periods. something to consider. So lots of really cool information in the Data Explorer, and we can have access to those informationals here as well. And so to figure out what's in this data set, let's first look at the info URL, the ERDAP info URL. So we'll say e.get_info_URL as a function and run that. And it tells us the URL of the information for this particular sensor on ERDAP's page. So it gives us all kinds of stuff like the attributes and the variables, which are here in green, and all of this stuff. Sometimes you don't know what the names of the variables are that you might want to find out of an instrument. So that's one way you can find them, is by asking for the URL for the info page inside of ERDAP. You can read this into a data frame by saying info, let's say _df equals PD, so it's pandas.read_CSV, and we'll say e.get_info_URL. We'll ask it to provide its response as a CSV. So now we have info_df. Now we have a data frame with all of those things that we just looked at inside of Python. And let's say we just want to look at the variables. So we could say, since we're working on pandas now, we can say info _data frame, where info the row type equals a variable. So now we've filtered that list, that data frame, where row type equals a variable, and this is a list of all the variables that this instrument has for us. So it's got latitude, longitude, and depth. These don't change really. They might change a little bit from deployment to deployment. I'm not sure. They certainly shouldn't change when the instrument's deployed. We talked about the tilt and the Y tilt, and then also the pressure. We're going to look at these data here specifically. So since we want the pressure, and we want to look at those as a function of time, we're going to extract just the time and the pressure.
Tim,
So
before you do that, Shima has a question.
Hi,
How do
Shima.
you know if the data is calibrated? If not, how do you get the calibration info?
Good question. How do I know if the data is calibrated? Shima, you can talk to me. What do you mean by how do I know if the data is calibrated?
Hi, Tim.
Hi, Shima.
Good presentation. Thank you. Yeah, I just want to know if you know, how do you know the data is calibrated or it's just a raw data? And if it's not calibrated, how do you get that?
Well, this instrument is providing calibrated data. So there's data cals information in the instrument page regarding the data and all kinds of things about how the data are collected at the instruments themselves, and then the calibration coefficients are here. For most instruments, if you're getting pressure and it's labeled with pressure, it's going to be calibrated to pressure.
I see.
Yeah.
So for some instruments that, I know that hydrophone data is not available to the Data Explorer, but are there any other instruments like hydrophones that we get raw data and we get the calibration information separately? Or they're all calibrated here?
Well, I don't know the answer to that question.
Okay. But the bottom pressure is calibrated and we can find that in the more information tab, right?
Yeah, let me just jump in real quick, Tim. A really short answer that will be not perfect, but the basic idea is the metadata for the instrument should have a calibration date. If it doesn't, you can go to, for most instruments, the raw data server will have folders with calibration files from the vendor, and you can match up the cal files with the deployment date. So that's the worst case scenario. If you can't find the information, that you can get the raw calibration data from the raw data server.
Got it. Thank you.
Is that Al speaking? I can't see anyone's faces.
Yes, that was Al.
Thank you, Al. I really appreciate that. And if I get any other questions that I'm stumped on, also please, anyone, feel free to jump in. All right, so we're going to constrain what we're going to grab using this ERDAP object to just time and Bob press. This guy here and the time. I should point out, I hope maybe I didn't do that, but you know, when you type things in here and you want to run these cells, you hit Shift Enter to run them. Because otherwise, if you press Enter, you just get this new lines. That's just how you put extra things on a line. But by pressing Shift and Enter, you run the cell, and then you actually run the code. So we're also going to constrain our data by time. So we just can set up a constraint. Be equal to a dictionary where the first key is time is greater than or equal to, and the value here is going to be 2014 01 01 at the time of 000000Z. Okay, and I'll take that and I'll copy that, put that here. And I'll say I want this to be also time is going to be less than or equal to 2015. 15. We'll go all the way to the end of the year. 12/31. We'll go to just the next. We'll go 2016 01. There we go. 01 at midnight. I need a comma here. All right, so that's it. We're done. We've got this ERDAP object. We told it that we wanted to get this data set ID, and we told it that we wanted to limit to these variables, and we told it that we wanted to limit to this time. And then if we say like the bot pt underscore data frame equals e.2 underscore pandas, and it gives us a data frame, a pandas data frame. You know what? This is supposed to be PT, sorry. Bot PT underscore data frame equals e.2 pandas. I'll run that again. Is a data frame that looks like this. It's not supposed to look like that. Why is it not? Hang on a second. Why is it not?
Hi, Tim. Sorry to interrupt. I think when you have e dot variable equals, it needs to have an s, e dot variables.
Oh, thanks.
That might be it.
Yep. Thank you.
Thanks, Daria. Author of ERDAP here, and I was looking for a mistake and I couldn't find it. Thank you so much.
I've been messing around with it myself, so happy to help.
very much. Much appreciated. And if anyone sees these errors when they show up, I really appreciate you to help me. And this is the fun. This is part of the fun. Part of the fun is that you help me. I screw things up, and then you help me fix it. That's kind of how this goes. All right, so let's make a quick plot of this guy here. Oh, I didn't import matplotlib, did I? From matplotlib import pyplot PLT, and let's. I don't think you have to do this anymore. How about this? How about PLT dot RC params figure dot fig size equals 10. And then we'll just do bot pt dot plt, and that should plot a plot of the data. So these are the data plotted by observation number, because I haven't changed the index to the time, and I'm not going to do that because we're going to turn this into an X array anyways. Data frames are nice. They're really helpful. They have a lot of really good time series functionality, a lot of really helpful things. But I try to work inside of X-array if I can, and the reason is because it has the capacity to kind of carry around a lot more data that's relevant to earth science data a little bit better, and it allows you to merge other data sets into it to kind of hold lots of different data sets from different places all in one place. So instead of using or working with the data frame here, a pandas data frame, which is sort of tabular data, I'm going to change over and instead load these data as an X-array. So this is stuff that Philippe really helped me with over the last couple of days, because ErtaPy has a 2 X-array functionality. So instead of doing a 2 data frame, we can type bot pt underscore ds equals e.2 underscore X array, and then we get an X-ray data set that includes some other things in there that we didn't ask for, which is interesting, and I'm not quite sure about that because we got a station and a row size, but we did get our data. We also got latitude and longitude, which aren't going to change, so we're going to drop those in a second here.
Tim, do you mind if I say something about that particular display?
Yeah.
The data variable station, row size, and bot pressure, that's an artifact of ERDAP. That's how the metadata is laid out for the table depth response, which is what you have there. If you try to open that response, you probably get a more netCDF, NUG-like metadata that you expect. Or if you try to load that as grid depth, then you have probably virtually the same thing that you get if you're loading the netCDF file itself. Mm-hmm. So yeah, I mean, we had a long discussion with Bob about that, and I really don't know. I can't explain why ERDAP prefers that layout for the metadata on table depth, but I know it makes sense. There is a reason for that.
Okay. So let's do a couple things. First of all, the time is relative to the dimension name of obs, and if we swap times obs with time, everything seems to work better. So we'll say bot pt underscore ds equals yeah, and anything anyone wants to add like that, please feel free. Bot pt underscore ds dot swap underscore dims. This is some toil. We're doing toil right now. This is what we're hoping to never do, but we're doing it because we have to. So we're going to swap obs for time.
I think you called it DF again above.
Oh, I did. That's bad. let's change it back to DS because the data set. So let's do that. Thank you. Dictionary, so that needs to be a colon. So now we have time, and we have the bottom pressure tied here to time. And this has been decoded. So if you look at this here, you can see that these times are daytime 64s starting in the middle of 2014. All right, so let's drop that dimension time series. We don't need that. And once we drop that, then these all go away. So we'll say bot pt underscore ds equals bot pt. And there are other ways to do this. I'm doing just a complete reassignment, which is not the most efficient way of doing this, but sometimes it makes it easier rather than doing an in-place change. So bot pt underscore ds dot drop underscore dims and time series. Let's do that. And then we end up with totally what we want, which is an X-ray data set with dimensions of time, coordinates of time that are daytime 64s, and then bottom pressure, which are floats, 64 floats. And then we also remember kept all of these attributes that are related to these data, which can be very useful going forward. Kinds of stuff.
And for our guests, I would just draw everybody's attention to the chat box where there's an interesting discussion about how to find calibration related data.
Great. All right, so let's use HPPlot. So I like to use HPPlot when I can because it has gives nice interactive plots, but it does make the plots big and hard to save, and we might have to turn off autosave on your Jupyter lab as soon as we do this, because it can throw an error all the time when it's trying to autosave these HPPlots. So we'll say import HPPlot.xarray, and then we can do a bot pt underscore ds dot bot press. So this is how we index or access the data array that's called bot press in here. I'll close this. Let's close that. So this is how we access this variable, and we'll just type HPPlot. Shows the data. Hopefully, similar to what we had before, except that now we can interact with it. So with the controls over here, we can zoom in and look at some of these pressure data. And as you can see, there's a tidal signal on those data like we would expect. And we also have this event here, which we're going to look at. Xarray makes slicing really easy. So if you want to slice into the data, you can do something like bot pt underscore ds. See, this is what you might show up for you here. This 413 response. That's because we put this on the screen, and I don't know, something doesn't like that. And so if you go up here to settings and uncheck autosave of the document, it won't try to save this thing, and it will be fine. That's an artifact of Binder. Those problems usually don't exist on a real Pangeo system because they've been sort of sorted, and you can't save your data anyways, or at least you can't. It's hard. It's not. This isn't going to be there for you when you come back, so it's okay if you don't save the data. Remember, everything that we're doing here and everything you're typing in can be accessed from the GitHub repo.
Tim, before you go on, Dawn has a question. Are these?
Hi, Dawn.
Dawn,
Hey. Yeah, I was just asking if all these bot PT data are like the full high resolution, or are these?
I don't think so. These are one. I believe these are 1 minute data.
Oh, okay.
Yeah, and that could be a good question for Dax since he works with these data. I don't know where the full res data are. They might not be on the Data Explorer yet.
Okay.
I'm not sure if they are. I don't know if that's true. But when you hit it like this, you get 1 minute data.
I see. Okay.
And so
Yeah, that's my impression as well, Don. Whenever we used the old method for pulling them in, we had to downsample to get to 1 minute. I think that the ERDAP only serves
Okay.
a slightly downsampled version.
Okay. Thank you.
we're going to be solving that problem in the next few months. We have a student that's working on about PT data, and once we get all of this figured out, we're going to figure out how to get the full res data.
Awesome.
I don't know if we have to go back to the raw data server or to M2M or something like that.
Yeah, because right now the way to access the full is through M2M, and that's about it. So I don't know if there's another way that's different. Okay.
Hey, Tim,
Not that I'm aware of.
Tim, there's a staging area that feeds Data Explorer that has the full res already generated. You don't need to go to M2M. This is Jeff.
It's like a staging for the ERDAP
It's the gold, we call it the gold server, right? That you can download that or you can attach to it. It's what you're attaching to in that PLC. It's not in ERDAP.
Right. It's not in ERDAP.
Oh, okay.
And Melanie has a question as well.
I was just wondering if you're gonna later on mention, or so there's inevitably gaps in the time series at turnarounds or whatever. And so for a gap there, like you can see, I don't know, close to the second tick mark, where it looks like it's either linearly interpolated across the gap or there's just no data points for those times. I was wondering whether you could clarify which of those is being done in these data sets that are being served.
Oh, yeah. So these data here are not being interpolated. This is just a line plot, so it's connecting.
Okay. Yeah. So when there are gaps, there's just time jumps. So the time variable is not regularly spaced. Is that right?
I believe that's true. In the data set, there are time gaps, and I don't believe there's NANs there for where there would be times but no data. But that's something we can solve, and we're going to merge a data set into this in a second here.
Okay.
That has completely different times, and they will live happily together with those NANs being in there.
Okay.
NANs can be a pain in some cases, but there's a lot of ways around working with NANs, right? There's a lot of ways to work with data that has NANs in it that you don't have to, where you can ignore NANs in a lot of cases. So a lot of functions will ignore NANs, or will have options to ignore NANs, or will have versions that ignore NANs.
Sure, I'm familiar with that in MATLAB, and I was just trying to understand what choices have been made in what to do about that in data that are being served. So this is helpful. Thanks.
Yeah, the data that's served have all the data points have all the times have data for these in this particular data set. And so this is not an interpolation. We haven't gotten that far yet.
Thanks.
If I plotted this as a scatter plot, there'd just be a blank spot here.
Yeah, thanks.
So let's see, I was going to slice these data. Maybe that's helpful. It's really an X-ray sort of thing to slice data. So for example, there's so many different kinds of time series operations that you can do inside of X-ray, including, aggregations, rolling means, counts, and group bys, and I mean it's a wonderful world to learn about if you're coming from MATLAB, because it allows you the opportunity to do all kinds of analysis and processing without having to think about all those things like, oh, how do I keep the time around? How do I make sure that it doesn't operate on the wrong thing? It's really smart about what it operates on. It's really, keeping the coordinates out of the sort of mix or sampling the coordinates in the right way or the way that you ask it to. In order to keep the data lined up with where the coordinates were, a lot of bookkeeping kinds of things that we used to do in MATLAB by hand. You don't have to really do any work. So once you kind of embrace the pandas / X-array time series operation world, and there's a couple of really good websites on that. If you type into Google pandas time series functionality, I think. Time series functionality. Google that. It is. So there's a website that's dedicated.
It's always a good day when things are okay.
Okay. Some things I'm talking to her. The time series functionality of both X-ray and pandas are enormous and huge. And once you embrace them, you can start really doing away with all that bookkeeping stuff. All right, let's. Oh, you know why? Because I said this is why. She perked up because I said that word right there. All right, what are we gonna do? Let's slice these data real quick. So let's do bot pt underscore ds. Why did I name these? I named these this way for a reason. I promise you. Bot press. So we're going to select the data array out of the data series, right? And we're going to select something from those based on the time. So we're going to say time is going to be a slice that goes from 2015, let's say 05, 01 to 2015, 07, 01. Let's 15, 07, 01. There we go. We can just HPPlot. The other thing that you'll notice when we plotted this thing, right? When we type HPPlot or plot, which will do the matplotlib plot, is that it made this beautiful plot that has the axes labeled, right, with the values that we're plotting, the times all set up here, right? And it gets even cooler as things get more complicated, for it to kind of keep track of these things and know exactly what or oftentimes know what you're trying to do or what you're trying to show. It chooses things like what kind of plot to make, right? So some cases it will choose to make a scatter plot when it thinks scatter plot's better, or even a bar plot when it thinks bar plot's better, and you can change that. But the ability to just kind of plot things and look at them and have all the labels access or axis, the axis is labeled without thinking about it is really nice. And that comes from, I should point out, setting up your X-array really nicely, right? So I did a little bit of work here to make sure that, time was indexed to a dimension called time, and that the data were properly linked to the time coordinate. Because once you get all of that sort of sorted and figured out, and we'll do that again in a little bit with the earthquake data, then a lot of those things with more of those bookkeeping issues go away. All right, let's do a quick rolling window on these data. So let's say we want to try to remove, really roughly, without a huge amount of work, this tidal signal from these data. We can apply a rolling mean, so we can do sort of boxcar rolling mean, which is a really simple way of doing a filter. We could apply a filter. We could set up a function that might filter these data using Butterworth filter, and then use the X-array map function to map a function onto all of the different variables or the ones that we choose, and filter them, or apply any kind of function we want. And when we do that, it keeps track of what's a variable, what's a coordinate, and it applies the functions to variables, not coordinates, and keeps track of all kinds of nice things. So let's do that right now. We'll say that we want bot pt underscore rolling equal bot pt underscore dataset dot rolling. We're gonna do a rolling window mean on 2-week data. So since we have 1 second samples, we'll say we want the time to equal the time window to be equal to 60 times 24 times 7. So that's a week. And we want we want to say that we have to have a full data set in the window in order to give a result. So we'll say min underscore periods equals, we'll say the same thing. So we'll say if there's any missing data in the window, don't give us an answer. 24 times 7. And then we'll say that we want to get a result from the center of the window. So we'll say center equals true, Boolean, and then from that we will take the mean of this rolling object. So what this returns is a rolling object, and the rolling object is this object that can be operated on, right? So it's really like, it's not a new data set, it's a new sort of animal, right, that gives you rolling windows, and you can apply things to it. You can do things to these windows. You can apply other functions. You can get counts of the number of things inside the windows. You get all kinds of things, or you can do mapping of functions. We're just going to do something real simple, which is take the mean of each of these windows in the center of the window in the window sizes that are 1 week. So we'll say mean, and that'll give us the rolling mean. Now we actually have this. Since we did the mean on this, this will actually provide us with a new data array, and it shouldn't take that long. So I'm not quite sure what's going on here. A little bit nervous. Oh, it's back. So bot pt underscore rolling is a new data set. Right? So even though this rolling thing was a new object called a rolling object or a rolling window object or something like that, once you apply a function to it, then it returns you a new data set. The new data set retains the coordinates of time for the center of the windows, and it has the block pressure values that are the mean of the window, and you can see that like it put a bunch of nans in the beginning because the first windows are not going to have enough data in them according to our min period function. And then we can plot this really easily by saying bot pt underscore rolling dot bot HPPlot. It'll plot the rolling average of the data that we just found. So here is a data set of pressure with the titles signal mostly removed. And it provided us with NANs here and here, and I don't know what's going on here. All right. So let's combine it with another data set. So we're going to go outside of OOI a little bit here and use an use an earthquake catalog that was generated by William Wilcock using OOI data. So OOI has seismometers out on the axial caldera, a big network of them, and William Wilcock has a system that automatically locates earthquakes using the seismometer data. So the seismometer data from OOI goes to IRIS. You can access those raw data there, but if you really want earthquake locations, you have to rely for the time being on William and his work to automate this process. And I have some information on this in the main notebook. But for now, because right now, I don't know, I think William's at sea or something, and his website is offline. What I did was I grabbed the latest one from him, or Dax did, and downloaded it and put it directly into this repo. So this is not ideal, but this is what it is, and this is where it is. So you actually have the data here, and I've got the raw file, which is this hypo-inverse 71 file. I'm gonna show that to you. It's super weird. And I parsed it because the date's super weird, and then I saved it as a pickle file. So we'll do that. We'll just look at these data real quick. So we'll say that the EQS_URL equals hypo71.dat. And then we'll just let's see here. Do this. I don't want to do this. We're running out of time. I'm going to copy this out of the notebook. Well, let's see what happens if I don't do that, because I'm not going to really work with this at all. Let's just see what happens if pandas reads it. EQS equals pd.read_csv of EQS_URL. Let's see what happens. No, didn't like that. Okay, EQS_URL. Okay, so you can take a look at this. The other way we can look at this is to, since I don't want to go through the trouble of typing all that stuff in, you go and you can pull up a terminal window and you can this is what a hypo-inverse 71 file looks like. It's a real fantastic number because it has the first column is year is four year digits, 2 months and a day, and then it switches over to hour, minute, and then it switches over to second. So it's sort of got this all globbed together like that. But I wrote a little function to parse that, and you can see that in the main notebook in the repo. We're not going to fiddle with that in this presentation today because I think I don't want to run out of time. What we'll do is we'll just load the pickle file that I provided. So also inside of this repo is the same data pickled and kind of cleaned up so that if you use pandas to read the pickle file, then that's good enough for now. If you want to get into all of the aim and enjoyment that was involved with parsing that, we can talk about that another time. So let's use pandas .read_pickle. Pickle is a sort of file type that's a real easy, kind of quick way of saving like a data frame without doing too much work or thinking too much about what has to happen when it gets reread back in. We'll read this PKL file, so hypo71.pkl, and then print out the, just run that, and then print out EQS_df.head to see the first few lines. And what you can see here is that there are times here in the index with latitudes, longitudes, depths, and magnitude of a whole bunch of earthquakes. How many earthquakes are there? If we do when EQS_df, you'll see that there are 151,191 earthquakes. Pretty good number over the last 7 years detected by the system and located. So they had to be big enough to be detectable and locatable. Are there any questions right now before we go on? All right, so let's take this data frame and turn it into an X-ray. So we'll say EQS. This is why I named these things this way. So I have EQS underscore data set now equals the EQS underscore data frame, and we'll say 2 underscore X array. So pandas gives us a function to turn a data frame into an X array, and that works really nicely, but it's not going to be quite perfect. We're going to have to fix that. Now we have a data set, and the data set comes in almost as we would want, right? It's got time as a coordinate, and it's got depth and magnitude linked to that time, but it also has lat and lon as a variable. Lat and lon are not variables. They're typically coordinates. Almost always you want a latitude and longitude, time, sometimes depth to be coordinates, not depth, not data variables. So let's move those into data. Let's move those into coordinates. So we can say just assign EQS underscore DS to be the same thing, which is EQS underscore DS dot set underscore coords, 2 O's. And here we provide an iterable where we're gonna provide the list of whatever we want to move into coordinates. So we'll say lat and lon. Now, if we look at EQS underscore DS, now this is going to look the way we want it to look. So it's really, really helpful when you're working with X-ray to think really hard about what this is showing you here. Right? I ask my students a lot to explore this and to really deeply understand it, to think really carefully about it, because if you get this, if you screw up the structure of your X-ray, then a lot of things don't happen the way you want them to happen. But if you get your coordinates in the right place and you have everybody linked together in the right way, then all kinds of really fun things happen. And so now we have an X-ray that's pretty much the way we want to look at it. Let's plot these data. So how about EQS underscore DS? We'll plot the magnitudes, since we can plot whatever. Since we're not, oh sure, we'll plot the moment magnitudes. HPPlot dot scatter. Okay, and see what happens. I forgot to put data shade. All right, so what happened? We've got the moments, magnitudes plotted against the longitude. So that was a choice that X-ray made for us. I would have to say that is not the right choice. What we want to do is we want to plot the magnitudes against time. So in order to do that, we just say X equals time. The other thing I want to do is turn data shade on. So we will have a data shade plot. So we can type data shade equals true. And this will give us a data shader plot. Warnings, I don't know if those are from some kind of new version, complaining about some other version. But here are the data from the most recent earthquake catalog from about the beginning of 2015 all the way through just a couple of weeks ago. So it's pretty interesting plot and interesting data. Let's look and see how the earthquake data compared to the data that we just downloaded from OOI. So let's merge them. So this is a really cool thing that X-ray does really nicely, is merge data sets. So we'll say all underscore data set equals, and we'll use an X-array function directly, X-array dot merge. We'll provide an iterable of data sets that we want to merge. So we have EQS underscore DS, and we want to have also bot PT underscore DS, right? So these are two data sets. One is the earthquakes, one is the pressure, and we're going to merge them into a new data set and call that one all of the data. we have a new data set, a new X-ray data set with the coordinates that are the same as before, right? It's merged in into a single time vector where the times were interlaced, and NaNs are included in the variables where there's no times for each time. So here we have, let's say, for example, a bunch of pressure data, right, that goes back all the way to 2014. And if you remember looking at the earthquake data, the earthquake data doesn't start until 2015. So there's a whole bunch of NaNs that are going to be thrown in there for the depth and the magnitude of the earthquakes. But we have pressure during those time periods. So this is a pretty sweet functionality of X-ray, in my opinion, is the ability to merge data sets. And when you start merging, many data sets, this starts to get really difficult. There's a lot of bookkeeping to do when you do this stuff, but not with X-ray. Basically just figures it out, puts them all together, interleaves them properly. And there's a couple of options that we didn't talk about that can give you more control, fine control over what you're going to get out of this, throwaway data where you don't have, throwaway data where you don't have data on all your variables and things like that. And the reason you might want to keep these all together like this in a single data set is because you might want to, basically do, calculations between these different variables in ways that you really need to have them lined up properly to do. I don't know what you might want to do.
I have a quick question for you, Tim.
Go ahead.
This is Melanie. So if you merged, if you had a lat long coordinate associated with the bottom pressure data, and if it wasn't quite the same as the one for the earthquake data, would it have put NaNs in? Like how would it have merged those as well? Similarly to what it's doing for time, I assume?
Yeah, I mean, it's doing it here, right? Because here it's already doing that here, even though we don't have latent longs for pressure. It's giving pressure to latent longs associated with it that are NaNs, because for every data variable entry, there's an entry in the coordinates, and if there's no coordinate there for it, then it will get taken in. And that will happen if you merge two data sets with lat and long. Right? They'll get NaNs where the other guys don't have the data, but the other guys do have the data.
Okay, got it.
They're lined up and they're there.
Yeah.
And they and it's really convenient to have. It's really a convenient way of doing it, because that way, your time dimension, has enough space in it for all your data.
Yeah, thanks.
Tim, just a time check. We have about 10, 12 more minutes.
All right. Yeah, we have to end a little bit early today because of another talk. I will make another couple of plots here with these data together, and then maybe we'll do some daily counts. I don't think we're going to get to, looks like we're not even going to get to, I don't even know if we're going to get to mapping these data. It's okay. We were hoping to go slow, and I hope you don't mind that we went slow like this. In my view, if you click through a notebook for people, it's just too hard for everybody to figure it out. So why don't we make a plot showing both of these things together? Oh, did it not show up here? Huh. Oh no. Oh, I see. We're gonna have to do. Let's do the daily counts real quick. we'll do the daily counts and then call it quits. All right, so let's make daily counts of earthquakes. So this is another cool thing that you can do with X-array. Count equals all underscore data set. So this is the data set we just created from the merge. We'll take the magnitudes out and we'll resample on a time scale that is 1 day. Okay, so this is another object that gets generated by a resample from this data set. We'll say we want to resample at 1 day. And what happens when we do that? We get this data, we get this object that's a resample object, right? Just like we did before. I didn't show you what the type was of the buyer, maybe it was a resample previously. But this resample object is a kind of object that you can also run things on. And so in this case, we're going to do something very simple. We've resampled the data on a 1 day time frame, and resample will provide a new data set, or a new data array in this case, which has a different number of values in it because it's resampling, right? So it's changing the number of observations to on the 1 day time scale, and on each of those daily time scales, I'm going to ask for a count. I'm going to count up all the values that are on in one single day. Okay, so now we're going to get a data array which is one piece of a data set, right? A data set is basically a collection of data arrays. So since we took this data array out, the magnitude data array out, and we're resampling it, it provided us back a new data array, but that has completely different set of timestamps. Right, the timestamps are by day, so it only has 2,655 stamps, and I had to convince myself that that was the right number of timestamps, but it is for about 7 years. There's about 2,600 days, and so we have a number of earthquakes that happened every day over this time period. You kind of get that information here. You sort of can tell there's a lot of earthquakes here, but there's no count associated with it. We can plot the counts. So daily underscore count dot plot will show us the numbers of earthquakes that happen per day over this time period. And you can see there's a huge number right here, 8,000. And we can plot all of these together, including the pressure data that we just had, by using some matplotlib stuff. So we'll say fig ax1 equals plt dot subplots. And we'll say ax1 dot bar is the daily count. And we're going to have to change this to a data series in this case, because this is one thing that X-array doesn't do, is slice and bar plot the way that pandas does. So we're going to take this daily count array and make it a data frame, pandas series by using the toSeries function. And then we're going to slice out 2015. And we are going to take the index, and we're going to make a bar plot with daily count. Dot two series. We're going to slice out 2015. I'm going to take the values. We're going to say that we want the width.
Tim, does it matter that you have a comma after fig?
After what?
Fig,
Yes, that's we want.
that's correct.
Yeah. Yeah, so so this is this subplots returns a list, and this is how we sort of get the two elements of the list that get returned by that function.
Thank you.
So there's the bar plot that we're gonna overlay the pressure on. So we'll say AX2 equals AX1 dot twin X, and so that gives us a new overlay plot with the X values of AX1 laying onto AX2. So we'll say, and this is Matplotlib, by the way, not HPPlot. It's pretty hard to do this, the fancy stuff in HPPlot, but it's not possible. So we'll take that rolling function that we made, right? And we'll also make that a series. So we'll say 2 series. And we will snag 2015 out of that. And we'll change the color to equal cyan. Good. Semicolon, you don't need that. Put it there so it doesn't output. So now we have plotted a bunch of earthquake data, right? Histograms or counts, bar plot of the counts of daily data from this from these earthquake catalog, and we plotted against pressure. So what's going on with the pressure? We didn't really talk about that very much, but this is pressure. So that means when the pressure goes up, the instrument goes down, right? If the instrument goes down in the water column, the pressure will go up, and it goes down by quite a lot. I think a couple of meters in this case, where the seafloor is kind of pressure is going down, right? The pressures in this instrument is going down because the seafloor is going up. This is like when the volcano is inflating, and then over this time period in 2015, there was a huge amount of earthquake activity, which culminated on a single day, I think, about a whole day or so of extreme earthquake activity while the earthquake erupted. And while the earthquake was erupting, there's this huge amount of earthquakes, and and over that course of that day, the volcano deflated. So the pressures went up as the volcano deflated and the seafloor instrument went down into the water column. And so you can see that here. And this is a really interesting data set because it is one example of what we've been finding at axial seamount, which is that it tends to be a sort of thresholding aspect of the eruption cycle. When the seafloor inflates to a certain height, or plus or minus, this or that amount, a lot of times that will be the point at which the earthquake erupts. And it's kind of done this in a cyclical fashion over the last couple of decades, erupting every, I don't know, 5 to 10 years or something like that. And the volcano now, so this is back in 2015, is still inflating, and it's been inflating, and it's kind of changing its rate of inflation over time. But a lot of predictions suggest that in the next year or so, we might have another one of these eruptions, and it'll be really exciting to be there for a new eruption with all of the instruments out there, the cameras, and all of these other sensors that can give scientists like you opportunities to engage with large numbers of data like these, and hopefully learn more about how the Earth works. There's a bunch of other cool stuff in the repo, including how to map these data really nicely. There's not a lot of stuff on Dask in the repo, but there is a really cool set of, or a really cool notebook in that repo showing how to search OOI data and also the IUS data ERDAP as together at the same time. That's this one here. I'll run through that, but you can go and take a look at that if you are interested in that kind of thing. But since we are at 12:30, I will just end this here and ask if there are any questions. I'm not connected anymore.
You're getting claps. You're getting claps and thumbs ups in the chat.
Oh, is Rich Signal still on the call?
Yes, he is. I think. Yes, he is. Feel free to unmute yourself, please. But I'd like to say, Tim, that was really great. Gosh, we could have a week-long seminar on this. It would be really wonderful. Maybe we can twist your arm and have you do another. But any remaining questions? Tim, did you disappear?
Nope, I'm here.
Oh,
Okay.
he's still here.
Okay. So with that, I'd really like to say thank you. Thanks to all participants, and we have to do this again.
Thanks, everyone. Have a nice day.
Thank you, Tim.
Thanks, Tim.
Yeah, thanks very much. That was helpful.
Bye all.